The Nobel Prize in Physics. Who won? What's the science? And why should I care? All that in under 3 minutes on Science Wrap. Rainer Weiss, Barry C. Barish and Kip S. Thorne for decisive contributions to the LIGO detector and the observation of gravitational waves. These guys were key players in the development of LIGO, the Laser Interferometer Gravitational Wave Observatory. Gravitational waves are literally bends in space-time. They're formed when mass accelerates. For example, when two black holes are spinning at faster and faster and faster until they eventually collide. What then happens is they send ripples out through the universe. As these ripples spread out throughout the universe, they carry with them a particular type of energy called gravitational radiation. Kind of like a surfer being carried to shore on a wave. But unlike that wave, these tiny ripples are really hard to see. First, you need to cancel out all that background noise. What LIGO does is it fires laser beams down two arms which are at 90 degrees from each other. At the end of each of those arms, there's a mirror that bounces that light back. If there's just background noise, the light comes back at exactly the same time, the light waves cancel each other out, and you don't get any signal reading. That's the interference part, interferometer. If, however, there's a gravitational wave in that background noise, the light beams don't come back at the same time, the waves don't match up, and what you get is extra light, and that's what we can measure to detect those gravitational waves. We were already looking at some really cool things to understand the universe. Things like cosmic rays, electromagnetic radiation, and neutrinos. You can kind of think of these like objects lying on a piece of fabric, the fabric of the universe. What LIGO allows us to do is to be able to measure gravitational waves also provide direct evidence that black holes exist. The tricky thing about black holes is that they don't give off any light, and light is what we normally measure when we're trying to observe the universe. Instead, we can study its gravitational effects using those gravitational waves.